Assalamu alaikum everyone. This is lecture 14 on Control System Engineering 1. We are discussing chapter 5, reduction of multiple subsystems. In the last class, we finished discussing the block diagram reduction. In this class, we'll be covering two topics. The first topic is analysis and design of feedback systems. Once we convert the system using the block diagram transform reduction, whenever we have a reduced system, sometimes we may have a unity feedback system as well. So a similar scenario will have something like this: unity feedback system. And if you look at the forward path gain here, you'll realize this is basically similar to the transfer function we derive for electromechanical system. Only the fact is that the value of alpha is here replaced by A. Okay, so negative feedback is been discussed in general. So this is your C of S, this is your R of S, and then the appropriate signs are there. Now, if you look at this transfer function, also we know how to find out the reduction of the block diagram reduction method for the feedback system. Is formula is very simple. You say this is our G of S for our path gain. I think it will be better to use a different color. So we can call this one forward path gain as G of S, and whenever we in general represent the feedback transfer function, we use T of S, and the formula is very simple: G of S divided by, which is forward path transfer function, 1 plus forward path transfer function and feedback transfer function. In this case, the feedback transfer function is a unity feedback system, so feedback transfer function is 1. So we'll have very simple thing, something like this: G of S, 1 plus G of S. And now if you put the values of the G of S from this system that we have drawn, a unity feedback system, that is K by S into S plus A, just multiply, you can also multiply. So SS square plus AS divided by 1 plus K SS square plus AS. So if we simplify the denominator a bit, keep the numerator as it is, K SS square K by S square plus AS, and the numerator we have S square plus AS plus K by S square plus AS. So you can cancel the common factors from both the numerator and the denominator. What we are going to get is K by S square plus AS plus K. So this is your after applying the block diagram reduction, this is your closed loop transfer function. So I call this one as closed loop transfer function T of S. Okay. Now, after finding, now as you can see, there is a factor K here. The factor K here is can be considered as a gain. Now, this can be a way of designing this feedback system. So, and what are the roots of this system? Basically, as we know, the property of the transient response that we expect is basically generated from the root. So basically, S square plus AS plus K, if you set it equal to 0, Then this will give you the two roots s12 equal to minus b by 2, that is a by minus a by 2 plus minus b square, that is a square minus 4k, okay, divided by twice a, that is 2. Okay, so this is the formula. So now based on the value of the k, we can have different conditions. So one condition can be k equal to 0. In that case, we have two different location of, so three condition basically, k equal to 0 will give you two different location, minus a by 2 plus something and minus a by 2 minus something. So on the same uh, real axis in two different location you are having it. So that actually gives you over damped scenario, over damped response. And now if a square is equal to 4k, that means k equal to a square by 4. If this is the scenario, then only both of them are on the same location. So basically, we can find the critically damped condition, critically damped condition. And the other one is if the value of k is greater than a square by 4, in that case, definitely this magnitude will be negative. Negative of the root will be actually have imaginary portion. So that will be your under damped scenario, under damped scenario. Okay, so we have something like this. Okay, so as you can see, by changing the value of k, you can achieve different responses. Now, whatever the design criteria is given to you, or you decided for a particular system, based on that, you can actually vary the value of k. And in third case, the formula will actually reverse S12 will be minus a by 2 plus minus j 4k minus a square by 2. So this is what you're going to get. Okay, so after our understanding that depending on the value of the k, we can have different solution. Let's look at one example, example 5.3, transient response, finding the transient response. So basically a system is given, similar system is provided with corresponding values 25 by s into s plus 5. Okay, so unity feedback system, this is your output and input, negative feedback. So now what you can see here, what they're asking is to figure out is you have to find out for this particular system, you have to find out peak time, so TP. Then you have to figure out what is the value of percent overshoot, and then the settling time TS. So first thing first, we have to find out the TS, closed loop transfer function, TS. TS is already, we know how to calculate it. Okay, so basically 25 by s square plus 5s plus 25. Now here omega n, if you now find similarity between this one and omega n square by s square plus twice zeta omega n s plus omega n square. So omega n square is equal to 25. That gives us omega n equal to 5 and twice zeta omega n equal to 5, from which we can find out the value of the zeta, that is 0.5. Okay, so sorry, 0.5. Okay, now based on these two values, the rest of the thing is just applying the formula pi by omega n root over 1 minus zeta square. That will give you approximately 0.726 seconds. Then you have percent overshoot equal to e to the power minus zeta pi divided by root over 1 minus zeta square into 100. That will give you 16% approximately. And also the settling time is 4 by zeta omega n approximately. So 1.6 seconds. Okay, so this is, so we haven't done any designing actually, just we have used the block diagram reduction technique to find out TS, and based on that we calculated the values, okay. But if you want to now actually want to have a design problem, so gain design for transient response, something like this you want to do, gain design for transient response. Okay, so now the gain is not provided, similar system, rather gain is kept constant as a k. So k by s plus 5. Now they have asked you to figure something out. What should be the value of the gain k for some special transient response that we are looking for. Okay, so let's see what they want. They want us to design the value of k for the unity feedback system so that the system will respond with 10% overshoot. So to maintain 10% overshoot, you have to figure out what should be the value of k. So this is our question. Now, gain adjustment. So T of S, same as before, k by s square plus 5s plus k. Now, what do you know? So this k is nothing but your omega n square, and this 5 is nothing but twice zeta omega n. So twice zeta omega n equal to 5. So zeta omega n equal to 2.5. Okay, so zeta is basically 2.5 by omega n. So omega n is nothing but, here we can say omega n is root over k. So 2.5 by root over k is your zeta. Okay, now percent overshoot is actually related with your zeta. So zeta equal to minus ln percent overshoot by 100 divided by root over pi square plus ln square percent overshoot by 100. Is it okay? So now if you put the value of percent overshoot is 10, then what you are going to get is 0.591. Okay, so 2.5 by root over k is actually 0.591. So if you just manipulate a bit, what we are going to get is k equal to 17.9. Okay, so this design problem specifically looks for a specific percent overshoot. But if somebody asks you whether it is possible to also control the settling time for this particular case, so what should be your answer for that? So as you can see, only the value of the k we can control, change it. But for the percent overshoot, for the settling time, you know that settling time is related to your sigma d, isn't it? So sigma d here is nothing but 5 by 2, which is fixed, which is not dependent on the value k. So for this particular case, it is not possible to actually control the value of TS. TS will be as it is. We cannot actually change it. Okay, so similar thing you can actually see in your example, skill assessment example 5.2. Let me just give you a hint how to do it. Skill assessment example 5.2. So here, Unity feedback system is given with forward path. Sometimes they will not give you the block. You have to realize what is the block. So they have just given you the forward path gain 16 by S plus A. So based on that, we can say T of S will be 16 by SS square plus AS plus 16. Okay, so now what they are asking is what should be the value of A to yield a closed loop system response that have 5% overshoot. So 5% overshoot you have to bring, and for 5% overshoot, what should be the value of A? This is what is your task for this particular example. So as you can see, similar thing you have to apply. So what we know is omega n. This time we know omega n is root over 16, that is 4. So your zeta, twice zeta omega n, twice zeta omega, twice zeta omega n equal to A. So this is what you have to figure out. So you already know the what should be the value of zeta based on that formula that we have just used, the minus ln divided by pi square ln. So this is what you know, omega n you already know. So if you figure out those values, you are going to find A equal to 5.52 to yield a percent overshoot of 5%. Okay, so very fairly simple. Now next comes your article 5.4, which is the other technique, that is signal flow graphs. Signal flow graphs. Okay, so in the previous system, in case of your block diagram reduction, basically the system was represented by a block, and your signal is represented by arrow, as well as two other component was there, summing junction and pickup point. But here we have only two component. One is a node, and we have a arrow or branch. Okay, so basically for the signal flow diagram, system is represented by a line with an arrow. Okay, so we call it branch. Okay, so you have to give the transfer function, any transfer function, say G1, G2, G3, H1, whatever it is, you have to give it using this arrow or branch. And the signal will be represented by, signal will be represented by, okay, so signal will be represented by a node. So the node, so maybe your the input, output, so or some other node. In general node is VS we represent. So V1, V2, V3, or yeah, RS, CS. So any signal will be actually represented by the node, and the system is represented by your arrow, or we call it as branch. Okay, so this is branch, this is node. Okay, now let's say we have a system something like this. What about the summing junction and all that? So if you have a summing junction, So definitely you'll have signs we are associated with the summing junctions. Okay. So we have say plus, we have minus, something like this. So this plus and minus will be actually going to the branch. Okay. So the branch that is coming, say this is the prior to that one, you have a G1, maybe G1S. Here maybe X1S, something like this. Then maybe some other signal. Signal is now node. Say this is your RS. This is your XS. Okay. So now RS will be node. So RS is node. Now G1 with the summing junction, we have a plus. So you have G1S as a plus. Okay, and now this will be also another node. So both the signal is going to the same node, and now it is starting node is x1 the signal, and then the system, the negative sign will be coming here. So negative, say this is x1s, or maybe some common factor like g1, g2, g3, or h1, h2, h3. So this is how the negative sign or positive sign is actually associated with the system. Okay, so it's included in the branch. And a node is actually the summing of all the inputs. Okay, so what is mean by that? The summation of all the inputs. Say we have a system something like this. There is three signal coming to this one. Then we have three output lines as well. So based on the arrow basically. So all three arrow coming to the same node. So basically all three is coming to this node, say VS, and then they are leaving. So these are called, let's say output one, CS1, C12S, C2S, and C3S. And say these are your inputs, R1S, R2S, R3S. Then you have the gain here, say G1S minus G2S minus, G3S. So actually we can also drop the S part because it can complicate the system. So say G4, G5 minus G6. So how actually it is represented? So V, what is V? V is the summation of the all inputs. So V, we can write something like this, Vs equal to, so the multiplication of R and G. So R1, G1 plus, second one is minus, we have a minus sign. So minus R2, G2 plus R3, G3. So this is very simple. So any node is actually the summation of all the input, and every node is containing whatever the value that is have after the summation. It has been forwarded to all the four output paths. Okay, so now if you want to say figure out what is C1s. So C1s is V is multiplied with G. So basically Vs multiplied with G4s. Okay, so basically this whole thing, that is R1, G1 minus R2, G2 plus R3, G3, the whole thing you multiply by G4, then you are going to get the output. Okay, so same thing will be happening for your C2, C3, and it is just based on the value of your uh, system transfer function, or whether there's a positive or negative sign. Based on that, you can also, we also have to include that. Like let us try to figure out what is C3. So C3 will be basically V multiplied by minus G6. So basically you will have a minus sign with R1, G1 minus R2, G2 plus R3, G3 into G6. Okay, so this is how you have to find out the output lines. So idea is very, very simple. So to proceed with this signal flow graph, let us first check with the familiar forms that we have seen in the block diagram reduction, how actually we can convert those into signal flow diagram. Then gradually, actually, we'll also try to look how the rest of the analysis will be carried. So say we have seen that cascade form, cascade. So in the cascade form, we have the blocks in series. Okay, so we have to identify actually how many nodes we have. So this is actually G1, G2, G3. Okay, and you had your input RS and you had your output CS. So you actually have to identify the node. So this is one node, say V1S maybe. This is your V2 node, V2S, and V3 is basically output. So basically, as you can see, we can easily have to identify the node. The input is a signal as well. So it will be one node. So this is your RS. Then this is your V1S. This is your V2S. And this is your CS. So in between the nodes, you just add the system arrows or branches. So basically this is your G1S. This is your G2S and this is your G3S. Okay, so if you have a pattern like this, you can also simply multiply those three together to find out. Formula is same. So R1, RS, CS. So you just simply can multiply all of them together, G1, G2, G3. So this is cascade. Now, if you have parallel, then what to do? Parallel form. The parallel form, we learned something like this. We have pick off points, then we have transfer functions, as well as we have the summing junction. Okay, so something like this was there. So based on your sign, you have to be careful about the sign, but we are just assuming that all of them are positive for now, but you can also assume any one of them negative at any time, no problem with it. So G1, G2, G3, RS, CS. Okay, so you have to identify the nodes. So definitely this is one node, this is other node. So they are same, this is same. So here you can actually take one node V1, you can take it another node V2, you can take it another node V3. So how can we have a equivalent model? So this is your RS, then you have V1, then you have V2, then you have V3, and you have the output CS. Is it okay? So now this portion is relatively easier. You just add the arrow and G1. Now, if you have a negative sign somewhere here, you have a negative sign, then you can easily incorporate that negative sign here with minus G2. Okay, so this is your G3. So this is your RS. Now, what about the output? How they will be connected? So in the summing junction, it is generally based on your value. Actually, you can also take instead of taking the minus sign here, we can also take it with a gain value 1. So if it is a plus, then it is 1. If it is a minus, then it is minus 1. and if it is again plus 1, so this is 1. So this is how we can represent. But eventually, it is becoming same thing, even though the summing junction, to understand the properly what is summing junction, we're making it V1, V2, V3, but eventually it is the only a magnitude of 1 you have to incorporate. So what we can do here is we can actually make them a single node. So this is your G1. If you multiply those two, because in the using the cascade, you can multiply those two. Then this is your minus G2, and this is your G3. Okay, RS, yes. What about the equivalent? Same as before. So equivalent will be, if you want, you can actually G1 minus G2 plus G3. But we are going to be using one method called Mason's rule. So for that, these are actually not necessary. Only sometimes the cascading thing we have to apply. Apart from that, most of the thing is actually remains as it is. Just we have to convert it to a signal flow diagram. So next thing that we are going to see is the feedback. So in the feedback form, feedback, what we have is, sorry, I started with the signal flow. Let's draw the block diagram first, then we go for the signal flow diagram. Okay, so this is your G of S simplified version based on which we actually derived the feedback formula. So use that one. This is your HS, and this is your CS. Now again, first thing first, identify the nodes. So basically we have one node here, E, error or actuating signal. So that is E. And then we have C is already there, so we can actually introduce another one here, say V1. But eventually what we are going to see is that V will eventually also vanish. Okay, so just for simplicity, just assume that this is V here. Now let us take it to the signal flow graph. So RS, then you have E, then you have CS, then you have say V1. So E2 CS goes through G of S, and then from C to V1, we can easily say that this one is going as HS, and the summing junction, as we said, we can represent by a gain of 1 based on the value of, based on the sign. So if the sign is plus, then 1. If the sign is minus, then maybe minus 1. Okay, so now this H, so let me just put the signals, all the signals here. So based on the value of H and minus 1 is in cascade, so they can be multiplied together. So eventually what we are going to get is something like this. One value of RS going with your GS to E, then it goes to GS to CS, and then you have a minus H of S. Okay, so this is your block diagram, sorry, signal for representation of your feedback. Now, if you want, you can apply the formula as before, and then what you can have is the transfer function G of S 1 plus G of S H of S. But as I said, we are going to use the Mason's rule. So because of that Mason's rule, we don't have to actually use these formulas anymore. So it has a unique formula. So this is all about the simple systems, but I think in the example 5.2 we had a critical one. So in the example 5.2, uh, from that one, let us try to bring that block diagram, and let's see how can we actually you reduce that one into a signal flow graph. Okay, I think let me bring that one first. Okay, so it is always time consuming to draw, but if we can take the help of okay, so this is the system was example 5.2. So now they already in the example 5.2 they have given the nodes, so it will be helpful for us. So as you can see, there is R1, V1, V2, V3, V4, V5. Then in the feedback you have V6, okay, V7, V8. So let us try to plot all the nodes first. Keep all the nodes. So basically RS. This is your RS. Then you have V1, V1S, V2S, V3S, V4S, V5S, and finally you have CS. Okay, now next is in the downside, I think we have VCX. Okay, and here V7S, and here we have V8S. Okay, so let's try to convert it. First of all, as we said, summing junction, you have summing junction can be given by a gain of 1 if the sign is positive, so we are giving a gain of 1. If the sign is negative, the gain will be -1. And then from V1 to V3, it's easier. So G1S. Then V2 to V3, we have another summing junction with the plus sign. So basically 1. Then here you have a negative sign, so basically -1. And then V3 to V4. V2 to V4 is basically we have G2. So G2S. And then we have another summing junction, so with the gain 1. Okay. And also, as you can see, from V3 to the summing junction, there is another one. So from V3, we can actually draw to that summing junction here with a gain of 1. Okay, so then from V5 to output, we have G3. So this is your G3. And from output C to V8, we actually have H3, H3S, and then to this summing junction, V5 actually, we have a negative value, negative feedback, -1. So from V4, there is two paths going, one going to V7 with a gain of H2S, and another one goes to this one. Okay, so you have something like this, and it is actually H1. Yes. So this is essentially the signal flow graph, but but what we can do is we can actually simplify a bit because some cascading thing is available. So actually you can eliminate some of the nodes, like as you can see here. So this whole branch can be multiplied together. Okay, so two branches there with their corresponding gain, so that this one can be vanished. Similarly, V6 can be vanished, V7 can be vanished, as well as V8 can be vanished. So the smaller the number of the signal, it's actually better for us. So that is why we take it from input to the V1. So RS to V1 with a gain of 1. Then we go directly to V3. Okay, so eliminating the V2, we are going to V3, V3S. So V3 to V4, we have G2S. Okay, then V5, we are going to V5. So this is V4S, this is V5S, and now from V3 we have a path going there. So you take it from there, and from V4 there is a feedback path coming here, multiplying together. So basically it is becoming minus H2, and another one, it is actually going to V1 directly from that same location. Okay, so that is your minus H1 S, and then from V5 it is going to through G3S to your output G3S, and also there is one of them. Okay, CS, this is your minus H3S. So this is your overall signal flow graph. So now we know if the block diagram is given, then how actually to convert it to a signal flow graph. Basically, idea is very simple. Idea is to find out all the nodes of your block diagram, and once you know all the nodes, you just connect those with your systems. So that should help you to figure out how to obtain the signal flow graph. The next thing is, if you have the signal flow graph, then how to apply the formula to find out a single block transfer function, single transfer function, basically input and output. What in this case we are interested is input you have, output you have, only one uh, gain block. Okay, so this is what we are interested in this particular case. So you have to figure out this quantity. So for that, actually, one formula is given by Mason. So this is known as Mason's rule. Mason's rule. And the formula is very honest, simple looking formula. The formula is G of S equal to C of S by R of S equal to summation of K. K is the number of path, forward path, TK, forward path gain, del K divided by del. Very simple looking formula. So here K is number of forward path, number of forward path. TK is kth forward path gain. Forward path gain. Okay, so what is del? Del is a bit complicated thing to understand. Del is said 1 minus summation of loop gains minus summation of non-touching loop gains, non-touching loop gains, two at a time, two at a time. Then the signs will be, sorry, the signs will be alternative. So first one is minus, then the plus, then again minus, then summation of non-touching loop, touching loop gain, three at a time, three at a time, then plus number of non-touching loop gains, four at a time. So it will continue as long as we can take. Now, what is del k? Del k is from del, we have to subtract the loop gains, those who are actually touching the k path. So summation of loop gain terms, loop gain terms that are touching, that are touching the forward path, forward path. Okay, so a lot of theory, a lot of writing. So basically, let me explain it with an example. Then all these quantities will be understood. Then how to apply the formula, that will be relatively simpler. So let us look at one example. What are gains? What are loop gains? Okay, so all that I'll be discussing with that example. So we have one example. Drawing actually takes time, so let me again take help of the book so that I can bring that picture so that it will be easier for you. It will be less time consuming as well. So okay, so let us bring it here. Okay, so this is your a particular signal flow is given. This one is cut. This is actually C6S. So now from this figure, let us try to understand what is meant by forward path. So forward path is very simple idea. Starting from the input to output, how many combination of paths possible? So like here, as you can see, starting from here, one straight line goes to the output. So this is one forward path. Okay, so this I just follow the arrows, arrows, arrows. So this is one forward path. So is there any other forward path? Now again follow the arrow. This is second forward path. Okay, it's slightly different with a single different branch will also bring a forward path. So in this particular case, what is the value of k? K is 2. We have two forward path. And now what is forward path gain? So we'll have T1, we'll have T2. So the gain of all the system in a path is forward path gain. So say the red one is T1. So red one is T1. So what is the gain of the red one? G1, G2, we are dropping the S, G3, G4, G5, G7. So this is one forward path. And what is the other forward path? G1, G2, G3, G4, G6, and G7. So though this is the only difference, but these are two different forward paths. and T1 and T2 is forward path gain. So this is T been explained. Now loop gain. What is loop gain? So what is loop? That definition should come first. The loop is the product of starting from one node, following the arrow. If you come back to the same node without multiple repetition of the nodes, right? Just once you have to take all the nodes. So let's say this is this is following this arrow. This is one. You're coming back here. So this is one loop. Okay. So the gain of this one is known as loop gain. So how many loop you have to figure out. So this is one loop we have. Then you can start it from here. Then you can actually come back through this one. So this is your loop two. So this is one. This is two. Now, is there any other loop? So you can go straight. Then again, you can come back. So this is your loop three. So is there any other loop? Yes, we can go in this way, then we can go in that way, then we can come back. So this is your loop four. So this is all four combination possible. Okay, so loop gains. What are the loop gains? Number one is this one, say this is number one. So gain of that one. So G2 H1 is your loop gain of that one. So number two is this smaller one here. So this is actually G4 H2. So G4 H2. Then number three is going straight, then coming back. So basically G4, G5, and H3. What is loop? Loop 4 is going upwards. So G4, G6, G4, G6, then H3. So these are the individual loop gains. Okay. So four loop gain we have. Next thing, I think, what we have non-touching cases. Non-touching, what is mean by the non-touching? So this is, so you have to take the loops, those who are not touching each other. That means they don't share any node. So that is what is called non-touching. So you have to take non-touching loop two at a time. Then how many non-touching loop? Three at a time. So this is what you have to check. So for that one, I think let's take it again, so it will be helpful. Okay, so now how many loop we already calculated? We have one loop here, we have two loop here, we have three loop here, then we have four loop. Okay, so two at a time. So their corresponding gain. So how many two at a time is possible? So first of all, this one and this one is, they're not touching, they're not sharing any nodes, so they can be one combination. So we can write that their corresponding gain is two at a time gain is G2 H1 and G4 H2. So this is one combination, two at a time. Next combination can be this one with the third one. Okay, so that will give us G2 H1, then G4 G5 H3. Okay, and the fourth combination possible is again with this one and the fourth one. So sorry, the third combination. So we are going to get G2 H1, then you have G4 G6, the top one is G6 and H3. So is there any other two combination? Because this one, 2 and 3 is sharing this whole branch as well as this two node. So 2 and 4 is also sharing this node, also this branch. So they cannot be isolated. So this is only three combination possible where you can take two loops at a time, two non-touching loops at a time. So is there any possibility of three non-touching loops? Definitely not in this particular case. So this is what we are going to get as a two non. So this is where you have to stop because of the fact that we cannot have three at a time or four at a time. So maximum whatever we can find. So this is what you have to figure out. So what is your transfer function? The transfer function says the different location difficult to find now. So transfer function g of s is basically uh, summation of summation of t and del. Okay, so one thing we haven't calculated is del k. Okay, so del k, we have to find out del. What is del? So del is basically, let's write it here. It will be easier. Del equal to 1 minus all the loop gains. So we already calculated what are the loop gains. So all the loop gains, G to H1, and then G4 plus G4 H2 plus G4 G5 H3 plus G4 G6 H3 plus all the non-touching loops two at a time. So two at a time we already calculated. So G2 H1 is the common, then you have G4 H2 plus G2 H1 G4 G5 H3 plus G2 H1 G4 G6 H3. So this is del. And what is del 1 and what is del 2? So del k basically. So del 1 and del 2. What it says that from the value of the del, you have to calculate from the value of the del, you have to subtract all the loop gains that are touching that forward path. So say first forward path is straight away this one. Okay. So now it is touching this slope, it's touching this slope, it is touching this slope as well as that slope. So all the loops they are actually touching. So that is why all the gains will be subtracted. So what will be left is only the one because all of them will be subtracted. So only one will be left. Okay, so this value is 1. Similarly, what will be your del 2? Del 2 is also same thing because of the fact that the del, even though we are moving upwards, but up to this point we are following the same path, then we are following this path. So basically it is also touching this slope, this slope, this slope, this slope, all loops. So del minus all the loop gains, basically all individual loop gains, then non-touching cases, everyone is there touching. So this is also 1. So what is our formula here then? So our formula here will be T1 del 1 plus T2 del 2 divided by your del. So we already know what is del. You can put the value of the del here, and we already calculated what is T1 and T2. So you can put the value of T1 and T2, and these two are actually 1, del 1 and del 2. So this is your single block transfer function, the required thing. Is it okay? So this is how you have to apply the Mason's rule. So once you have that signal flow diagram, the Mason's applying the Mason rule is very, very simple. So I will try to actually discuss a few more example. What I think at least two more example. Also, I'll try to take help of the Bakshi book so that if we can have some additional content that can help us to understand the signal flow graph well. Let me conclude the class here, even though it may be a bit short compared to the last classes, but I think you're also overburdened by too many classes. So keep it, let me stop here. Then we'll start with small one to few examples with the signal flow graph in the next class. Then maybe we'll shift to the next chapter, inshallah.